Suppose we approximate the sum of a convergent series S, which is the sum from n equals 1 to infinity of all the terms in the sequence. If we approximate this by summing only the first k terms, then what we're saying is that the true sum, as in the sum of all of the terms in the sequence, is approximately equal to the sum of the first k terms in the sequence. Now, this won't always be true. Certain conditions need to be satisfied in order for this to be reasonably accurate. And obviously, it should go without saying that the more terms you have in the approximate sum, the more accurate your approximation is going to be. So if a function f is continuous, positive and decreasing on the interval between k and infinity, we can apply the integral test. Remember, the integral test says if the improper integral converges, then the sum to infinity of the sequence will also converge, or the series will converge. So the error in the approximation, which we're going to call Rk, is, as you would expect, it's the true sum, as in the sum of all of the terms, minus the sum of the first k terms, as in it's the actual sum of every single term all the way to infinity, which doesn't really make sense, minus the sum that you did as an approximation by adding up the first k terms. So what we're saying, the error, again, this is just, it's a very complicated way of writing something that's fairly obvious when you say it in words. We're saying that this error is just the sum of the rest of the terms. So if you do the approximation by adding the first k terms, then the terms from k plus 1, k plus 2, k plus 3, all of those onwards must represent the error because they're the bits that you didn't include in the approximation. So this is an important result, this inequality, that the error can be bounded. Remember, this only works if f is continuous, positive, and decreasing on the interval from k to infinity. So the error is less than the integral from x equals k to infinity of f of x dx, but it is greater than the integral from x equals k plus 1 to infinity of f of x with respect to x. So here now we have a specific example. Suppose we can use the integral test to show that the sum from n equals 1 to infinity of an of a sequence is convergent. So if we can use the integral test, it means that f is continuous, positive, and decreasing on the interval from k to infinity. So suppose we can use the integral test to show that it's convergent, where an is some function of n. Part A, we need to show the inequality that I've just introduced. So show that the error in approximating the infinite series by adding up all of these terms up to the kth term, show that it satisfies the inequality where the error is less than the upper bound integral that I've just explained, and it's greater than the lower bound integral that I've just explained. So what we're going to do, we're going to think about drawing some rectangles. Okay, so this is part A, and then we will go on to decide how many terms we need for a specific series to estimate it to a given amount of accuracy. So what we're going to do, we're going to draw some rectangles, and we're going to draw the functional representation. Remember, it's positive. So everything's above the x-axis. It is continuous and it's decreasing. So it probably looks something like that. So this is our f of x. We know that the x-axis is going to always be below the function. And if we're looking at the whole thing, we'll probably have the y-axis somewhere over there. So when we actually do the approximation, well, we start with 1 and 2 and 3 and so on. And then we're going to go all the way up to some k. So this would be 1, 2, 3, 4. Remember, when you approximate a series with rectangles, it's like a Riemann sum, but every rectangle has a width of 1 because that just makes sense. Natural domain of a sequence is all the positive integers, right? So if x was 1, or if n was 1, thinking about the sequence, this would be a1, is this value here. If it was 2, well, this would be a2, and so on. And what you do, you add up a load of rectangles. So you might add up these rectangles, the uppers, or you might add up some lower rectangles, but you are definitely going to add rectangles. And then what we do, we cut it off at the kth term. So we get to here, and that is where our approximation ends. And what we do, I've not drawn mine brilliantly, but we assume, or we hope, that the rest of the terms are so small that they don't contribute significantly to the sum. So that's why it's reasonable to do that. And then after that, we have k plus 1, k plus 2, and so on. So these rectangles that we don't include, which may be upper, may be lower, they represent the error. So we're going to say we include everything up to k. After that, we stop and we don't include things anymore. So we are looking to show that a k plus 1 plus a k plus 2 plus a k plus 3 plus so on, all the way up to infinity, is less than this integral between k and infinity of f of x dx, but it's greater than this integral from k plus 1 to infinity of f of x dx. So if we just focus in on the end, as in at the end of the actual approximation, we can focus in on the bars and the integral after that, which represent the error. If we draw our nice continuous decreasing function, have a bit of a x-axis there. This is f of x. And we might go, say, might have a bar at k plus 1, k plus 2, k plus 3, and so on. And then we're going to draw bars up to here. So you always get a choice with rectangles. As in, for any given one, you can pick the upper bound like this, which will give you the largest possible area of the bars. Or you could pick the lower bar, if I can draw that, like this. So there's a difference between the area. The lower bars are always, for a continuous decreasing positive function, the lower rectangle is always underneath the line and the upper rectangle is above the line. So if we use the lower rectangles, which would represent this area here, so using the lower rectangles, if we compare it to the integral in question, if we draw this particular integral in green, so the integral from x equals k to infinity, well, that's going to be this area here, the green area. So you can see it will be all of the pink bits plus these little green bits that are not there. Using lower rectangles, Rk, the error, can be seen to be less than the integral from x equals k to infinity of f of x dx. So that's okay. Now we need to do something similar with the upper rectangles. We use an orange to represent the upper rectangles, so that would be this area here. So the upper rectangles cover all of that. So it's getting a bit messy, I do apologize. But using the upper rectangle, we're looking to show an overestimate. And we're comparing it to the integral from x equals k plus 1 to infinity. So that is going to be this integral here. All of that. So if I just shade that in. But obviously these rectangles will continue. If I just look at this, it's not going to be any different after that. It's just that this is the bit we happen to be looking at. So that is the integral that we're looking at, which is in black. So using upper rectangles, you can see that the integral between x equals k plus 1 and infinity of f of x dx, you can see that's clearly underneath the orange area. So the orange area includes all of the black bars plus a bit extra, and it's going to happen. It's going to be the same for every single bar. So that is less than rk. So if we put that together, that tells us that rk is less than the integral from x equals k to infinity of f of x dx, and it is greater than the integral from x equals k plus 1 to infinity of f of x dx. Now, if you're wondering, well, we could have sort of compared this upper rectangle bit, we could have taken the integral from k and it still would have been underneath, and we could have done something similar for the other one. Yes, you can, but if you just, I've obviously zoomed in so much. If you're considering an improper integral or a sum of an infinite series, a width of 1 is so minuscule in the grand scheme of things that it really doesn't make a massive impact on the calculation at all. But all you have to do is show the inequality is true, and we've conclusively done that. Although it might be a good idea to do the upper and lower diagrams separately, because you end up writing over things that you've done. Right, it's part B. Hence, that we're going to use this result that we've been given and that we've shown. Hence, determine the number of terms necessary to approximate the sum from n equals 1 to infinity of 1 over n cubed, correct to 2 decimal places. Okay, so part B, we want, so correct to 2 decimal places is correct to the nearest 0.01. Now, if you want something to be correct to the nearest 0.01, then you need your error to be less than half of that. If you think of how things round, this is a bounding thing. It's about upper and lower bounds when you round. So that means rk must be less than half of 0.01. If you think of 0.01 as being 0.010, rk needs to be less than 0.005. So if it's less than that, when we round it, it will be correct to 2 decimal places. And we know rk is always less than the integral from x equals k to infinity of f of x dx. So that needs to be less than 0.05. So the integral from x equals k to infinity of f of x. Now remember, the series we're talking about is 1 over n cubed. So the integral is going to be 1 over x cubed dx. So that is a value that we know the error is less than. So this needs to be less than 0.005. Okay, so if we're working that out, for an improper integral, we know that that means the limit as b approaches infinity of the integral between k and b of 1 over x cubed. So that's going to be x to the power minus 3, x to the power minus 3 dx. And that needs to be less than 0.005. Right, so if we want to integrate this, add 1 to the power, divide by the new power. So the lim as b approaches infinity of x to the power minus 2 over minus 2, which is the same as minus 1 over 2x squared, evaluated at b and k, and that needs to be less than 0.005. Okay, so now we need to just put it in. Remember, top limit, evaluated at the top limit minus evaluated at the bottom limit, so the lim as b approaches infinity of, well, it's going to be minus 1 over 2b squared minus 1 over 2k squared. So that's going to be plus 1 over 2k squared. And that needs to be, well, it's less than 0.005. So I think if we do this in a non-calculator way, that's 0.005 is 5 over 1,000, which we can simplify on the next line. That's going to be 1 over 200. So now we know, if you just consider this minus 1 over 2b squared, well, as b approaches infinity, 2b squared must also approach infinity. Minus 1 over 2b squared is going to approach 0. So that first term is just going to be 0. So that means 1 over 2k squared must be less than 5 over 1,000, we said was 1 over 200. So now at this point you could take reciprocals of both sides and flip the inequality, but I would say it's more likely that you're just going to move some stuff around. So we know everything's positive, we know k is positive, so k squared is definitely positive. So that's going to say k squared is greater than 200 over 2. 200 over 2 is 100 k squared, which must mean k must be greater than 10. If you think of the actual context of the problem we're solving, it says determine the number of terms necessary to approximate the sum from n equals 1 to infinity of 1 over n cubed, correct to 2 decimal places. So we need k to be greater than 10, has to be a whole number because it's a number of terms, can only be an integer. So we need 11 terms, or 11 terms are necessary. Okay, so once we have 11 terms, we will know that our series, or the sum of our series, is accurate to 1 decimal place, which isn't bad.